We spent the first two lectures building up ideas of parallelism from the hardware level. We talked about how SIMD style devices lend themselves towards data parallel programming. How MIMD style devices lend themselves towards task-based parallel programming. So remember, data parallel programming means running the same program on a whole bunch of different data at the same time. So you're effectively doing the same thing to many different data points. Whereas task parallelism means different processes can be doing completely different things. This week I'm going to introduce some general theory around parallelism. This is ways to help you think about algorithms and to think about complexity and about some of the classic problems that show up in parallel programming. There was a time when parallel programming was just a total mess. It was impossible to debug. There were these classic problems around non-determinism and race conditions and deadlocks that we'll talk about. To a large extent, these are now being resolved through particular styles of software engineering. So we now have standard design patterns. You might remember from second year, we talked about design patterns in the TSE module. So there's a whole collection of new design patterns that have shown up to help you with parallel programming and specifically to try and reduce some of these classic problems. So along the way I'll talk about languages used in parallel programming and how we might want to change the kinds of language we use, the kind of constructions we use, in particular to become more functional, to fit with ideas of parallelism. But we'll start by just reviewing some basic ideas from complexity theory. So hopefully this is just a refresher from what we may have done in the first year. Did we all do algorithms and complexity in the first year? Did game students do algorithms and complexity? Any game students? Who's a game student? Yeah, algorithms and complexity. Yeah, so complexity theory is going to change somewhat when we consider parallelism. Traditional complexity theory was developed quite a while ago, mostly in the 1960s, when it was assumed that everyone just had one CPU. And so when we write about an algorithm being order n squared, for example, we mean it's going to take order n squared time on a single CPU. So how is that going to change if you now have a parallel device? Let's review some basic notations used in complexity theory. We may want to talk about how long does it actually take to solve a task. Most tasks come with a size that we measure using n. And often n is the length of the number of, it's the number of bits in your input. Okay, it's the length of your input in bits. That's not the only way of measuring n, it's the most common one. So you might, for example, be trying to solve an optimization problem. You're saying find the binary number that makes this function as big or small as possible. And if you've only got 3 bits to search through, that's a simpler problem than if you've got 64 bits to search. So as n gets larger, the time taken to solve a task is typically going to increase. We usually measure time in terms of the number of basic operations available on your computer. Exactly what those are depends on what your computer is. Roughly, it's supposed to mean the number of assembly language instructions that are going to be executed. Obviously, different computers have different instruction sets, and those instructions can take different times to run. And so generally talking about T is unhelpful. Usually there's a bit too much information that goes into T. That's the exact number of instructions that need to run to execute your algorithm. What we tend to talk about instead are these order measurements. The letter O stands for order. So for example, an algorithm might be order n squared. That means it's going to take roughly n squared operations. We're not going to count exactly how many operations. In particular, we're going to throw away any multiples by a constant. And we're just going to say generally this algorithm scales according to n squared. Or it might scale according to 2 to the n. Or it might scale according to log n. Many people use these notations incorrectly. The letter O is often thrown around as the single measure of complexity. If you say an algorithm is big O n squared, that's often taken to mean it's going to scale with n squared. That's not quite what modern big O actually means. Often we're talking about this thing in the middle called big theta. Okay, that's the Greek letter theta, it's the letter th. Theta of n means the algorithm is going to scale according to n squared, or whatever the complexity is. If your algorithm is deterministic, if it's always going to run the same set of operations, this is all you need, because the algorithm will always take exactly the same length of time. If your algorithm has branches in it, so if it's got an if statement somewhere, then it's possible that the algorithm might take more time or less time, depending on what the input is. So in those cases, it doesn't make sense to say it always takes n squared, because there's going to be a best case scenario and there's going to be a worst case scenario. Yeah? Your algorithm might just check the input and say if the input is 1, then return true. Okay, so that's an instant calculation if the input is 1. But then it might say otherwise, go and do this huge NP hard thing that has a much higher complexity. So, as well as big theta, we can talk about big O and big omega. And these are the best known bounds we have on the best case scenario and on the worst case scenario. Okay? So, big O is actually bounding the worst case scenario. This has led to a lot of mismatched computer science over history. Most algorithms over history have been developed to create the best big O, which is making the worst case look as good as possible. What you find in practice in the real world is many problems come with a subset of data. You don't want to run your algorithm on every possible input. You want to run it on kinds of inputs that actually occur in the real world. And so using big O it's often led to pessimism, where algorithms actually can perform faster than you think they're going to if they're measured with big O. And then some books will also talk about little o and little omega, and these are just any other bounds we might have on the best case and the worst case. So you might have done a mathematical proof that shows the algorithm is going to take at least n squared time, but then someone else might do a proof that says it's going to take at least n cubed time, which is even worse. So in that case, you've got a lowercase bound, which is the first one, and then you've got the uppercase one, which is the best one you currently have. But if your algorithm is deterministic, they're going to meet in the middle. The best case and the worst case are the same, because there's no branches in your code, and it's always going to take the same length of time. So lots of books still throw around this big O notation, when arguably they really mean big theta. And especially when we do parallel algorithms using these design patterns, you'll see we try to avoid that kind of branching. We try to make these algorithms as deterministic as possible to make them easier to understand and debug. And so that means we can normally end up talking about big theta rather than having to talk about big O or big omega. So let's remind ourselves how we work with these notations. Let's say you are given a simple serial algorithm. This is a merge sort, right? You've all seen merge sort before? Yeah, basic sorting algorithm. Still a good sorting algorithm. Merge sort runs by taking a list of inputs and you split it into two, and you say go and sort the first half. You say go and sort the second half using recursion. So you now have two small lists, each of which are sorted, and then you go through this process where you look at the heads of the list and you say which one is the smallest, and you pick one element from each of the two sublists, and that makes your final list. So basic. To figure out the complexity of this, we derive a recurrence relation. Okay? So this is going to say that the time it takes to solve a size n problem. So in this case, n is the number of items in the list. Okay? It's the length of your Python list. You say the length of time it takes to sort n items is going to be 2 times however long it takes to sort n by 2 items plus n. Okay? And we're going to derive this by stepping through the code. We're going to annotate the code and say what is the complexity of each step here. When we recurse, when we call the same algorithm on two halves of the list, if the whole algorithm takes tn, then that is obviously going to take tn by 2. That's a call to exactly the same function, but we're giving it a different input, which is half as big as it started. So we know that whatever the time of this is, it's going to take half of it to run that line, and it's going to take another half of it to run that line. When we look down here, these simple list operations, so pushing and popping a list, we say these are order 1, so we don't care exactly how many CPU instructions it is, but it's a constant, it's not going to scale with n, so we call this order 1. You can see these are wrapped in an if statement. Potentially this could get us into big O and big omega territory. However, both branches of the if have the same complexity, right? You're going to pick one or other of the two sublists and pull its head off and put it into your result list. So it doesn't actually matter which branch you take, you're still going to end up with order 1 complexity for the whole of the if statement. And then you're going to iterate this if statement. You're going to do this n times over a loop. Okay, so if this takes order 1, the loop is going to take order n. And if you add all these complexities together, you can now see that this total time, the time for the whole function, is going to be 2 of these plus that. So you see time to run on n is 2 times time for n of 2 plus n. Okay, so this is called a recurrence relation. Once you have your recurrence relation, you now have to solve it. Okay? This is a mathematical equation, and we're going to solve it to find out what the complexity actually is. Since 1998, we have had this really super fast way of doing that called the Acrobazi theorem. You might have come across the master method in older textbooks. The Acrobazi theorem is a generalization of the master method, and it will just give you the complexity very quickly for a large class of recurrence relations. So if you're given any sort of recurrence relation like this that you've derived from your algorithm, the Acrobazi theorem says if you can write it in this form, so there's some function of x, or n we usually call it, some immediate function of n plus a sum of weighted recurrences. Okay? So look, in our case, we've got this bit, this is going to be the g, and we've got this bit, this is the recurrence, which is the function of t. So if you can write a function like that, and subject to some conditions, you can perform this operation. You can try and find a number. So you know A and B are given to you. You can go and find a number P to make this thing true, and then you plug it all into this expression, and it will just give you the complexity. Okay? If you're interested in how that works, here is a reference to the proof. But if you're just a user of complexity theory, this is all you do. So that looks abstract and scary. Here's an example showing you that it's actually really simple. So we started off with our recurrence relation. Okay, that's the thing we've derived by doing this. We're then going to plug it into this expression here, and we'll see g of n is just n. Okay, so this term is going to describe this term. Okay, g of x equals n. There is no h term. You can see the recurrence is just the function of n over 2. There's nothing getting added, so we know h is 0. We can see the number a is 2. That's the coefficient there. We can see the number b is a half. That's what we're multiplying n by in this side here. Okay, so we've just written our expression in the required form, and we've read off all of those little numbers. Okay, once we've done that, we just grind the crank. We go through the maths, and it'll give us the answer. So now we have to solve this thing. So we know A and B, we know that A is 2, we know that B is half. So to make that work, we've got to set B equals 1. Okay, that's going to make this picture. So now we've got all our values, including B. And now we just plug everything into this expression. So we do this little integration, if you can remember how to do integration. Plug your G in there. Remember G of n. Remember P is 1, so u to P plus 1 is 2. That's going to give you the integral of u over u squared, which is simplifies to the integral of 1 over u, which you might know is log u. Okay, if you remember a little bit of high school maths. There are also machine algebra programs that will just do these for you nowadays, if you don't like doing this yourself. So yeah, once you've got that, you can then shove it into this expression. We know that x to the p, we know p is 1, we know that x is n. So if you plug all that together, you're going to end up with the time is theta n log n. Right? And notice it's a big theta rather than a big O, because this is exact. It doesn't depend which branches we take through the program. So there are other ways to derive these as well. The Acrobatic theorem is kind of the latest and greatest, and it's very much plug and play. You just step 1 is you do this, you figure out your recurrence relation. Step 2, you write it in this form, and you just plug everything in, and it will give you the answer. In the olden days, you had to guess. You had to make an induction hypothesis. So you guessed that it was going to be n log n first, and then you try and prove that using induction. With the theorem, you don't have to do that anymore. So that's how we would analyze a serial algorithm. Okay? When we talk about a parallel algorithm, we've got to decide what it is we actually want to measure with complexity theory. And there are two interesting concepts that we might want to measure. One is called the work. That's the total amount of computation that gets done, and that is usually the same as on a serial machine. Okay? Often a parallel algorithm will just take the work that is done in series, and it will just do some of this simultaneously. So it's the same work, just being done at once. Whereas the span tells you if you had an infinite number of processors available and you could distribute work however you wanted, the span will tell you what's the time that the whole system takes to run. So it's equivalent to finding the longest worker. So say you've parallelized your algorithm over 10,000 cores. Some of those programs will branch, some will take more time than others. The bottleneck in the whole system is going to be the one processor that takes the longest time. Yeah, that's going to determine the time that the whole system takes to run. So that is called the span. So for example, say you have a really easy parallelization task, right? This is what is called trivial parallelization or data parallelization. We've just got 5 data items and we want to do the same processing on each one. Okay? If you do that in series, that is going to be order n. So in this case, n is 5. It's going to take you 5 ticks to do these things one after another like that. If you do it in parallel, the work is still order n, because there's still 5 jobs getting done, but the span is just going to be 1, which is incorrect on my slide. I should say only 1. Yeah, the span means the longest task run is just going to take 1 tick. So span doesn't tell you how long the thing actually takes on your computer, because your computer doesn't have an infinite number of processors, right? Your computer has some finite parallelization capacity, but it's a theoretical measure that shows you how parallelizable is your problem. So if you had all the parallel resources you could ever want, what's the fastest it could go? In practice, your algorithm might assume we've divided the work into 100,000 jobs, and your GPU can only run 20,000 jobs at a time. And so there's going to be this extra factor where you put maybe 5 batches of 20,000 jobs onto your GPU in series. Here's the correct figure. Yeah, this is for the serial machine, right? If you literally run one task after another, you're going to get order N. If you're in parallel, you're going to get order 1, because that's the length of the longest run through the parallel network. So you might remember this concept back from computer architecture, maybe, Amdahl's law. Anyone remember this? Amdahl's law is about how does a complete system speed up if you hot run one subcomponent of it. In architecture, we talked about it in the context of upgrading part of your computer system. If you swap out your hard disk, for example, for a super fast hard disk that goes 100 times faster, is that going to speed up your whole computer by a factor of 100? Yeah, probably not. It's going to speed it up a bit. It's going to speed up all the parts of the task that rely on the hard disk, but the rest of the computer stays the same. Or if you upgrade your CPU, it's going to speed up those tasks, but you move the bottleneck somewhere else, like the memory does. We can also make this Amdahl's law for parallelization. Most tasks that we create algorithms for will naturally have some component that is easily parallelizable, but they'll have other components that are inherently serial. So it's quite common, for example, to farm out a load of work to different cores to process the color of an individual pixel, for example, but then you might need to do something afterwards. You might then need to look at all the pixels together and find the average color, perhaps, across the whole image, and that part of the code is going to look more serial. So if you switch to a computer that has n processors, 20,000 processing elements in the GPU, you're not necessarily going to get a speed-up factor of 20,000 because part of your program is still serial and is still back. So Amdahl's law is a little equation that tells you what the speed-up factor is. You say your program has some fraction f, which is parallelizable. And that fraction of the program is going to get sped up by p, where p is the number of processors that you have available. Whereas this part of your program, 1 minus f, that's the fraction of your program that is not parallelizable, and that still takes as long to run as it did before. And so you'll typically see charts like this. So for some task, you have this value of f saying how parallelizable it is. So these are 4 different tasks with different levels of parallelizability. Great way to say it. And you'll see they scale differently. Like as you increase the number of processes, they'll all increase rapidly for a period, but they tend to level off after a while. So in all these tasks, there's not a whole lot of point in upgrading from 100 processes to 1,000, because you're hitting on these bottlenecks where the parallelizable part of the program isn't the interesting part. The bottleneck is now shifted to the serial part. So let's look at how we do an analysis on a parallel algorithm. This is the same merge sort we saw before, except can anyone spot the difference? What's changed in the algorithm? There's one symbol that has changed. This little guy. So all the other lines end with a semicolon, and semicolon means do one thing after another. This line ends with an ampersand, which is notating do 2 things in parallel. This isn't any particular language, it's just a nice notation to use for analysis. So what this means is we're going to run this line, then we're going to run these 2 lines simultaneously. And then when we get to the semicolon, that means we're waiting for them both to complete, and then we're going to carry on running in serial afterwards. And so what this is going to do is create a structure like this. We start off with a single process. When we get here to the ampersand, it's going to split. It's going to This is called forking a process. So now we have two processes that are running these two lines, and each of those is going to recurse again. Each of those is going to split into two. And each of those is going to split into two until you get down to the base case. And then you put everything back together again. This structure is called a fork join structure. Okay, you're doing a fork and then you're doing a join when the things come together. And if you use a language like Silk, you see the structure built into the language. In Silk it's called spawn and sink. This would be a spawn and this would be a sink. So let's say we want to analyze this algorithm then. We can do the same analysis in the code as we did before. We know this line is going to take time of n over 2. We know this stuff's going to take n. The difference though is that these two lines run at once. Okay? So instead of having two of them and adding up their time, we're just going to take one of them as the time. Okay? Because they're both going to run in parallel. So we now get a different recurrence relation. We now get time for n is time of n over 2 plus n. Yeah? Remember last time there was a cube. And if we plug these numbers into the acrobatic theorem, we will see that this algorithm is thus theta of n. Okay? So serial merge sort, we got n log n. In parallel, we can now do sorting in theta n time. Okay? It turns out you can actually make it go even faster because you could think about parallelizing this part as well. If you go and hot rod this, you can even get the thing down to theta of log n squares. Okay? Or how about the traveling salesperson problem? Yeah, it's the classic NP-hard problem. It's the classic NP-hard problem. The optimal algorithm for the traveling salesperson problem. Do we all know this problem? Yeah, you've got n cities, you know the distance between them. You've got to plan a route for your salesperson to visit each city and get the minimum distance for them to travel. The optimal algorithm is called the Bellman-Kopp algorithm, and it is known to have time and space complexities. Usually we talk about the time complexity, n squared 2 to the n. Notice this is non-polynomial, that's why the thing is NP-hard, because you've got 2 to the n in there. If you're interested, that's the actual algorithm itself. It roughly works by building up larger and larger subsets of cities. So you start off just with one city at a time, and then you say, what's the best way to get around 2 cities? What's the best way to get around 3 cities? It's dynamic programming. But you can see the structure of this algorithm has a bunch of loops. Yeah, in fact, it's got some very heavily nested loops. So if we parallelize the loops, we'll find that we dropped from being n squared 2 to the n down to n 2 to the n. Okay. So what do we notice about this speed up? What's the factor of speed up? Going from n squared 2 to the n times 2 to the n. Yeah? That n squared has turned into an n, so we've got a speed up of n. And if you think about it, that's usually the best speed up you're ever going to get out of a parallel algorithm. If you've got n processes available, you're going to divide the amount of time it takes by n. The work is the same, but the span is reduced by n. So notice this isn't going to help you with the p equals np problem, right? If the problem is np hard, it's still np hard after you've parallelized it. Because dividing by n isn't going to turn a non-polynomial problem into a polynomial problem. But it's still a nice speed up to have, yeah? If you're actually allocating timetables for n students in the university as an optimization problem. That might be the difference between it becoming tractable to actually run and being intractable. And that's exactly what we do. That's exactly what we use parallelization for, to solve that problem. That's why you're sitting in this room. You have been optimized into the optimal location. So, we can make all the theory much easier if we work with particular languages or language constructs. Traditional programming languages were developed in a time before parallel computing was a big thing, or was a necessary thing. And as such, they tend to conflate various ideas which have now become problematic. So for example, loops. Okay, we need to ban loops. We still teach loops to kids in schools, and we shouldn't do this anymore. The reason is that a loop conflates two different ideas together. Right? When you see something like this is for I in range 1 to 10. Right? Consider this one. Okay, here's a simple loop. In this loop, we're saying for I in range 1 to 10, go and do something with I. Yeah? So you might have a list. You might have a list of 10 elements, and you want the number 1 to be added to every item in the list. What you're really saying here is I've got 10 items, and I want them all doing. Right? I've got 10 different jobs, and I want all 10 of those jobs to go and get executed. And in this case, I don't care what order they're done in. You could do them all at the same time, you could do them starting at the end and working backwards, you could do them in a random order, it doesn't matter. This kind of loop is different. Okay? This kind of loop is called a dependent loop. So can you see what's the difference between this loop and this loop? So you see we have this variable a, okay? And a stands for accumulator. In this loop, the order that you execute it does matter, because each time you go around, we're going to do something to this global variable a. That changes the state of the whole system. So it means every iteration of the loop is seeing a different input value a, and it's outputting a different value a. So this loop is a very different kind of beast from this loop. Okay, this is not really a loop. This shouldn't be taught to children as a loop. This should be taught to children as what is called a map. Okay? And a map means I've got 10 jobs and I just want them all doing. Whereas this thing is called a dependent loop, and it means I really want them doing this serial order, this particular serial order. So this loop, well, this is really a map, and in some languages you can write it as a map. So this is a much better way to write a Python. If you're doing this kind of thing, you were actually writing it as a map. I'm saying, here's a function that takes X as input and adds 1 to it. Go and apply it simultaneously to all 4 of these items in the list. So this is nice and easy to parallelize. Yeah? And a good compiler may be able to do this automatically. It will see that map and it will just distribute it across the 32 CPU cores that you have, if you're lucky. Whereas this thing is an inherently serial program. There may be some clever way to rewrite the algorithm to make a parallel program that does the same thing, but you're not going to be able to parallelize it directly. So when we do parallel programming, it is useful to hold this distinction in our minds and to try and stop thinking about loops and think much more in terms of maps. While loops are even worse. So what's the difference between a for loop and a while loop in terms of this kind of theory? So a while loop is inherently serial, right? There's no way you can parallelize a while loop. The whole point of a while loop is that every time you go around, you check something. You check part of the state, and if it's true, then you go around again. You perform a while loop in series. It's an inherently serial operation. And every time you go around, you check and you say, am I going to go to the next part? So while loops are inherently dependent. Okay? And you can often write a while loop as a for loop, if you like. Okay? This is an equivalent loop. And that helps you to see the structure. You can see there's this state sitting in the background. So while loops are generally nasty constructions, right? If you study computation theory, like we were going to this year before we can logic and computation module, you would learn exactly why they are nasty. They have a different computational power to all the other constructs in the language. They're the constructs that give you church power, making your system into a church computer. But the cost of that power is that everything becomes difficult to prove. It becomes impossible to prove if programs are going to terminate in many cases. A halt. And you end up in this other world of computation where you don't know if your program is ever going to actually run or not, or if it's going to get stuck in an infinite loop. If it's going to get stuck in a blue screen of death, and it's a formally uncomputable problem to figure that out in this case. So there's actually lots of good reasons for not using while loops anyway. Okay, it's generally a bad habit. If you can find a way to express your program without a while loop, it's always best to do that anyway. There are some cases where you need whiles. Like if you're doing a real-time system that has to keep going round and round forever, you might want to say while true and keep going. But for everything else, they're generally bad. And when you write parallel programs, you're really going to try and avoid these because you can't parallelize the while loop. It's an inherently serial operation. So a good parallel programming tip is don't use while loops. Okay? Sometimes this is called total functional programming, if you do it this way. You end up with a formally weaker language. There are certain algorithms that you cannot express if you don't have while loop programming. But the upside is things behave better. How about if statements, okay? Let's say we have a program like this. We've got 3 hard functions, and hard means it takes a lot of time to compute. How can we make this program go faster? Well, we could execute all 3 functions simultaneously, right? Let's parallelize it like this. Remember, the ampersand means we're going to fork the process. We're going to do 2 things at once. In this case, we're going to do 3 things at once, right? We've got 2 ampersands. So look, we can replace this program with this. We're going to calculate all 3 functions simultaneously, okay? And then right at the end, we say, did you get true or false for B? If so, return A, otherwise return C. Okay, and at this point, this is going to run almost instantly, because that's just brilliant. So if you run this normally, it's going to take the time for 2 hard functions. If you run it in parallel, it's only going to take the time for 1 hard function. Okay? What could go wrong when we do this in a regular language? Okay? So some functions have side effects. If you're writing nice theoretical functions that really are functions, so the mathematical definition of the function is something that takes an input and it gives you an output and nothing else changes, right? That's what a real function is. Most languages don't work with real functions, they work with other things called procedures or methods. And a method, for example, will not only give you a return value, but it will have side effects. It can change the state of the computer in some way. Yeah? It might update the state of the world in the game, it might write a file, it's doing something outside, just giving you a return value. So the problem is, this might make your game character move left, and this might make your game character move right. Yeah? And this is reading the input and deciding what you're going to do. The problem is if you've got the side effects, both sets of side effects are going to execute. Yeah? And so your character will move left and right and not actually go anywhere. Yeah? So you can only get away with this kind of parallelization if you ban side effects from your functions. Okay? If you program in a language that has true functions, prove there are no side effects, then you can do this kind of parallelization. So look, these 3 tips, okay? Bin loops, use maps, don't use while loops, don't use side effect functions. If you ever study functional programming, this is basically the recipe for functional programming, right? And it's all those weird academic languages like Haskell and Standard ML that may have been forced upon you and you laugh at them for being impractical in the real world, but they turn out to be really, really useful for parallel programming because all the assumptions of functional programming map really nicely onto parallelization. So some of the research we have been doing here recently is about how can we automate that process with Python. This is a system we built. We take a Python program. Well, technically, this is a subset of Python. Okay, we're going to ban all those bad things I just told you about. Right? You're not allowed to use dependent loops. You're not allowed to use while, and you're not allowed side effects. So you're programming in a subset of Python. Right? We're going to compile your Python down in this case into an intermediate virtual machine language called SPIR-V. And SPIR-V is just a list of simple assignments. It's defining a bunch of variables, and each variable is some function of things you have computed before. So number 56 is a function of number 8. That's going to create a data flow graph. We can see how each variable depends on some variables that have been computed before it. And from that graph, we can read out the optimal parallelization for the whole program. Okay, so the program looks something like this. We can color in which register is being used, which variable is being used. And this will tell us everything that can be done in parallel. So we can be computing this at the same time as computing this. And then we take that data flow graph and we turn it into a bunch of logic gates, and then we go and fabricate a chip. And this chip executes a Python program without a CPU. Okay? This is the optimal amount of parallelization that can be done to your Python program. So that there's no concept of an instruction anymore. It's just the algorithm itself gets expressed purely at the architectural level, and it's going to flow as fast as possible through that data flow graph. And this is the kind of system you can then put on a robot to process a sensor, for example, where you need really fast reactions to the data coming in. But this is fundamentally enabled by thinking in terms of these functional programming structures. Okay, we've banned all the nasty parts of Python, all the stuff that has state or that has dependency. We've kept all the bits that look like Haskell, basically, and we found we can then make it go very, very fast at the architecture of that. So, in the olden days, parallel programming was really, really nasty. When I studied it, or it used to be called concurrent systems. The highlight of my undergrad degree was when we finally passed the parallel exam, and we went into the park and we just burned all the materials to do that module. We made a bonfire with the books and the lectures. No one ever wants to do this stuff again because it's so horrible. The reason it's so horrible is there are known cases where messes are created and they become very, very difficult to get right or to debug or to prove that they actually work. So one of these is called a race condition. Okay. This is a piece of code that could equally fit into my life as a hedge fund trader. You know, this is something we might do. A client comes in and they want to place an order for a stock, or it could fit into my life as a school's adventure game programmer, teacher. You know, this could be your Dungeons and Dragons character meeting an NPC, and they're going to trade some gold for a shield, and it's exactly the same problem you have in both cases. Let's say in both cases we're dealing with multiple processes. We've got multiple agents coming in parallel. If you're in a hedge fund, you've got different clients calling you up saying do this thing. If you're writing a multi-user dungeon, you've got different players who've dialed in over SSH and asking you to do things. And the problem here is you are this character, you are going to make a trade with this other character, the trader, and you're going to buy or sell this item for this price. Okay? So you're going to check your inventory. In this case, we're selling. Yeah, we've written it from the point of view of selling. We can check our inventory. Do we have this thing? Does the trader have the cash? If so, we're going to remove the item from our inventory. We're going to add it to the other player's inventory. Then we're going to add the price to our cash, and we're going to subtract the price from their cash. Yeah, that seems very straightforward. Yeah, that's the basic rule of this trade. Now the problem is you're trying to do this in a multi-user system with hundreds of people all dialing in at the same time, and you might get something like this. Here you've got two players A and B, and they're both trying to make a trade with player C. Right? They both want to trade the same stock, and they want to trade it at different prices. What you're going to get then is two executions of this same function will spin up in parallel. Right? They'll both start running at the same time. And exactly how they run, you basically have no idea. It's called non-determinism. And so, for example, one version of it is going to start removing this stock from your inventory, and then the second item comes in, and while you were removing it, it might have checked if you still had it, and it says true. Now it gets to here, and it's going to try and remove it again until it's gone. Yeah? Or equivalently, you might have, both of them might have run perfectly in parallel, and they both get to this line, and they're both going to try and increase your cash by 2 different prices. Okay? So this line is saying you had 10 cash, go and add 1 to it, that means you've got 11 cash. The other execution is saying you've got 10 cash, go and add 2 to it, that means you've got 12 cash. And so do you end up with 11 cash or 12? Both of those are the wrong answer, right? If there's 2 trades going on, you really want to end up with both of them getting added in, but there's no way to express that. And so this function is actually just a total mess. Okay? This is not going to work when you parallelize it. That's called a race condition. So what you really want to do is something like this. You want to put in a lock, or call it mutex, or mutual exclusion. You probably do something like this. You say, if the function is locked, you're not allowed to do anything, go and wait. And then when you get the lock, go and do this thing and release the lock. That means only one player at a time can go in and make a trade. There's still things that can go wrong with this. So both players might try to set the lock at the same time, for example. So you might need some hardware level support. And in OpenCL, for example, you're going to see that. That's called an atomic. That is hardware support to ensure that really only one player can have the lock at the same time. When you start putting in locks, that means everyone now has to queue. Okay, all these players want to do the trade, and they've got to queue to get into that protected critical region of the code. And in some cases, that's going to reduce your nice parallel program back to being a serial one again, as people take it in turns to go through the bottleneck. In even worse cases, you get problems like this. Okay, here are 5 philosophers sitting around a dining table. Okay, this is a famous parallel programming problem. And they represent processes, okay? And the knives, not knives, it's all forks. The forks represent resources that everyone's trying to get a lock on. So they're all trying to eat spaghetti, and to eat spaghetti, you've got to have 2 forks simultaneously, right? So your job as a philosopher is to try and get hold of these 2 forks and then do some eating. And when you finish eating, you can put them down. And notice the forks are shared, okay? So you get into these horrible deadlock situations. If each philosopher tries to grab 1 fork, they're all sitting there with 1 fork, no one can eat, no one's going to put the fork down, and the whole system grinds to a halt, right? And then that's how you get a blue screen of death. So you need to come up with algorithms to prevent that from occurring, to prevent deadlock. Okay? In 1971, Kaufman proved a theorem that tells us what those conditions are. There have to be 4 conditions all present. So mutexes have to exist. There's got to be this ability to hold a mutex and to wait. You're not allowed to take a resource off anyone else by force. And there's got to be a situation where everyone is waiting for everyone else. So in the olden days, the problem was to identify if a deadlock could arise and then deliberately try to break one of these conditions to get rid of it. You know, for example, have a rule that you can only pick up 2 forks at once rather than holding one. So that kind of programming was really, really nasty. Okay, doing anything with race conditions and with deadlocks basically led to this kind of problem. This is a slide from last year's TSC lecture. Okay, it's just hard. It's nice. What we have developed since then are these ideas of design patterns. Okay? To try and work around all these problems, we're going to define fixed design patterns, like we did in TSE for other kinds of programs. We're going to design a few fixed patterns, and we're going to try and program just in terms of those patterns. And the patterns are designed so that they ignore those problems, or they find ways to work around them. They tend to be very GPU or SIMD friendly. They tend to be very data parallelism friendly, although you could run them on task parallel systems as well. So what we're going to do in the next couple of lectures is study some of these patterns. Okay? And the basic pattern is called map. That just means forming out the same task to lots of processes on different data. You might have heard of the reduce pattern, the next heard of map reduce. That's a fusion of the map pattern and the reduce pattern, which became very famously in search engines during the 2010s, for example. But the idea of a pattern is what is going to bring sanity to this whole field, right? It's what is going to, like, you guys graduate and go in the park and not have to burn all your parallel programming textbooks, because we have a nice way of doing it now, right? We now have nice textbooks that keep you sane. They define these particular ways of programming that are going to work and are not going to lead to the race conditions or the deadlock. So we'll start looking at them next week. We'll do some of them in the workshops as well. We will be doing the workshops still in OpenCL, but remember the patterns can apply to anything. They can apply to all these other technologies like Silk and MPI, even ROS, if you're doing robotics. ROS is a parallel system. And you can take a pattern and you can use it to generate many different algorithms.